Section 3 of Chapter 3 describes formula weights. It gives definitions of some terms, and we'll see some examples of calculating formula weights and just one other sort of calculation we can do with formula weights. So the formula weight is the sum of all of the atomic weights of all atoms in a formula. Right, so that's what we have up here, the definition. My comment here, formula weight is agnostic with respect to the type of formula. It simply means it doesn't matter whether the formula we're looking at is an empirical formula or a molecular formula. Formula weight applies to any formula. Just count up the atoms, multiply the number of atoms by the weight of each atom, add it all up, that's the weight of the entire formula, and that's simply what we mean by a formula weight. Now, in the special case that the formula happens to be a molecular formula, then we can refer to the formula weight either as a formula weight, that's always correct, or we can refer to it as a molecular weight. And I very commonly use a formula weight, FW abbreviation, on tests. If you see a FW, that means formula weight. Molecular weight should only be used if the formula is in fact the formula of a molecule. Now down here we have another definition, the idea of a formula unit. A formula unit is simply the number of atoms present in a given formula, again without implying any special features of that formula. That is, this applies to any formula, be it empirical, molecular, whether it's an ionic substance or a molecular substance. We can always use formula unit to mean the set of atoms present in a given formula. So for example, calcium chloride is not a molecular substance, so it doesn't have a molecular weight, and it does not consist of molecules. There are no molecules of calcium chloride. However, I can use the term formula unit to refer to the set of atoms represented in the standard formula of calcium chloride, namely 1 calcium atom and 2 chlorine atoms. So let's do some examples. Let's calculate the formula weight of phosphoric acid. Again, this is a typical way of me asking a question. You have to remember the formula of phosphoric acid. If I were to ask you this on a test, there are some points for getting the correct formula for phosphoric acid, and there'll be points associated with calculating the formula weight correctly. So let's see. Phosphoric acid is H3PO4. So when I set up the formula weight, let's see if I can get my pen to work here. So the formula weight is going to be, well, we've got 3 hydrogens. I'm going to write it out algebraically so you can see exactly what I'm doing. I take 3 times the atomic weight of hydrogen. I add 1 times the atomic weight of phosphorus because there's only one of those in the formula. And then I see that there are 4 oxygens, so I take 4 times the atomic weight of oxygen. And then reading the values of those off our class periodic table, so we have enough significant figures and so that we use the same values here. This is equal to 3 times, let's see, the atomic weight of hydrogen is 1.00794 AMU. And then I add the atomic weight of phosphorus, which I look up on the periodic table, 30.97376, plus 4 times the atomic weight of oxygen, which is 15.9994. Add that all together. When I do that, I'm limited to 4 places after the decimal because of the significant figures in the atomic weight of oxygen. I'm adding numbers together, and I get 97.9952 AMU. So there's our formula weight. Let's do one more. Calculate the formula weight of yttrium dichromate. Again, you have to remember your naming so that you know what I'm talking about. Remember yttrium. Look at the periodic table to remind yourself it's in column 3, so it has a +3 charge. Dichromate ion is Cr2O7 with a -2 charge. And so our formula for yttrium dichromate, when we balance the charges, looks like Y2 Cr2O7 taken 3 times. So if I calculate the formula weight, again, here I'll do it in a shortcut manner. I'm not going to write it out algebraically. I see that I've got 2 yttriums. So I have 2 times, I look up the formula weight of yttrium. It's 90,584. It's an 8,4 AMU. Plus 6 times, I've got 2 times 3 chromiums, that's 6 times the chromium's weight, which is 51.9961 AMU. Plus, now I've got 7 times 3, or 21 oxygens, so 21 times the weight of oxygen, 15.9994 AMU. And then just plug it into my calculator. Quick check of my significant figures. Once again, oxygen or chromium limits me to 4 places after the decimal when I add these numbers together, and I get a final answer of 825.7756 AMU. Remember to round to the correct number of significant figures and include units on your final answers. One last thing that we want to talk about in this section is calculating the percent composition from a formula. And as I say on this slide, this is exactly what it sounds like. Just an application of the common idea of percentages to formulas. So the percent of an element in a formula, you just take the mass of the element in the formula, divide it by the total mass of the formula, and multiply it by 100% to convert it to a percentage. So if we calculate the percentage of oxygen in phosphoric acid to 5 significant figures, if I tell you to round to 5 significant figures, this is how we're going to set it up. We're going to use the formula weight that we just calculated from the previous slide for phosphoric acid, 97.9952 AMU. And then we'll calculate the percent oxygen by taking the number of oxygens, 4, times the mass of each oxygen. So this total quantity in the numerator gives us the mass of oxygen in the formula, divide by the mass of the total formula, multiply by 100%, round to 5 significant figures, and our answer will be 65.307%.